So, now let us see the transistor connections. So, in a transistor we have 3 terminals, and when a transistor is in use we give some input and we take some output. So, for input we require 2 terminals and for output we require 2 more terminals. So, total 4 terminals are required. So, we have only 3 inputs and we require 4. So, what we do, we take a terminal as a common terminal, and so there are 3 ways to in which we can make one terminal common. So, let us see it. So, this is the first case in which this is the base, and suppose this is emitter and this is the collector. So, this is collector and this is the emitter. So, what we do, so this is, so when this base is common, between this input, this is input and we have to take output. So, this mode is referred to as common base connection. So, this is the first type in which the base is common in input and output. So, input is provided here, input is provided between emitter and base, and output is provided between collector and base, and so this is the common in between these two. This is one type. Second is common emitter connection. So, in this connection, this emitter is common. So, in this here base, this is the base, this is the emitter and this is the collector. So, this is the output is here and we gave input here, input. So, here input is given across base and emitter, here base and emitter, and output is taken across emitter and base, emitter and collector. This is the collector and emitter. So, you see we have made this emitter common. So, this type of connection will be called common emitter connection. There is another mode that is called common collector connection. So, in common this is collector and this is your base and this is emitter, and you see here we give input here and we take output here. So, input is given over this base and collector, and output is taken over emitter and collector. So, this collector is the common. This is the common collector connection. So, we are interested only in this part. This is in our syllabus. This is commonly used common emitter connection. So, this is not in our syllabus. We will concentrate only in this part, common emitter configuration. So, now let us see what is a common emitter configuration, and we will study the characteristics of common emitter configuration. So, now this is common emitter characteristics. In order to study the common emitter characteristics, we design a circuit. Let us see how we can do so. So, this is my transistor in which this is common emitter, this is emitter. suppose this is base, this is base, this is emitter and this is collector. So, now here this is PNP type, this is PNP type, PNP type transistor. So, we keep here a micro ammeter to measure the base current. So, you see this arrow tells the direction of the current, this will give IE and IE here. So, this current here is IB in this and here you will get IC like this. So, now next we have a voltmeter here that will be used to measure this emitter base VBE voltage. The voltage between base and emitter will be measured by this voltmeter. And now you see I give a biasing here, this biasing has to be given here. So, this is forward biased. So, I have to keep this junction forward biased. How we can do so? This P should be connected to the positive one and this should be connected to the negative one. So, now this is variable. So, in order to study this bias and we slowly we increase and decrease. So, that arrow shows that this is we are going to vary the bias, this is this side. Next here again we have a voltmeter that measures this VCE, that is, so a voltmeter to measure VCE, and here I have a collector current for measuring collector current, that is in milliampere. The range of IC is milliamperes. Now, here I have to apply now bias, that also I can change. So, here you see this should be reversed bias, this is P side. So, it should be connected to N and the biasing should be more here, and that also can be varied according to our demand. So, this is the circuit, this is PNP. Now, I remove this PN things, so that my diagram should be neat and clean. So, this is PNP transistor which is common emitter, emitter is common in this side. So, this side circuit is called, this side is called input circuit, input circuit, and this side is output side, output circuit, output side or output circuit, anything we can call it. Now, common emitter characteristics means first we will study input circuit, input side or input characteristic, then output characteristic. What is input circuit? Input circuit means we will see how this IB varies with the changing voltage. When I vary this voltage, we connect this a cell and a rheostat, that means this is a cell with a rheostat. So, by rheostat we can change this, that means I can directly show it's a cell with a changing voltage level. So, and how much is the voltage, that can be measured here. So, how this current changes with base emitter when this is kept constant. When VC is kept constant at a constant value of VCE, how this base current will vary with its emitter base voltage, that we are going to study. So, please take down this diagram, this is very important. Now, let us see input characteristics. Input characteristics in common emitter configuration. Now, the variation of the plot of variation of IB, that is the base current, with respect to the VBE, that is the emitter base voltage at constant VCE is called input characteristics. Input characteristics. So, what we do? We plot a graph between VBE. Here we plot VBE, that is in volts, and here we have a current IB, that is in microamperes. With respect to, so this VC is constant. So, what we get at initially the current does not grow and then it grows linearly at some value of 0.7 for silicon or 0.3 for germanium. So, at some value, this below this value, this current does not grow at all, and thereafter the current grows up. So, what happens? So, what happens now? The input characteristic is similar to the characteristic of a forward biased PN junction. So, you see here, till the silicon or for 0.7 is for silicon, the potential barrier for the forward biased silicon crystal is 0.7, for germanium it is 0.3. So, till that condition is reached, till the barrier is reduced, the current flow does not take place. So, thus once this barrier potential, so once the barrier potential that is silicon 0.7 and germanium 0.3, once the barrier potential at the emitter base junction, once the barrier potential at the emitter base junction is reached by VBE, the current conduction begins and the curve becomes linear. So, the curve becomes linear. Now, you see there is a small difference between the characteristics of a forward biased PN junction and this. In a forward biased PN junction, this current is the whole current that emitter gives, but here it is a portion of the emitter current. You see, IB is a portion of the emitter current. You see, it is a portion, but if IE changes, accordingly will IB change. Since it is a portion, but the change of IE will be reflected in the change of IB. So that is why we also expect that IB also varies in the same way in which the PN junction current will vary. That is why we expect such graph. Next point important is, first please take down all this point. So, now further if the VC value is increased, then the current IB decreases. So, what happens? You see, if VCE is here, suppose I say 2 volts, this here I have reverse bias applied is 2 volt, suddenly I change to this 6 volts, VCE becomes 6 volts, the graph won't too much change, but slight change will be there. So, generally it is plotted for a single value. Let us see for what will happen if I plot for 2 values. So, you see the value of current is here. So, when further if VC is increased, then the current IB decreases for a particular value of VBE. So, let us see what happens actually at that time. So, you see this is my transistor, this is my transistor, this is suppose P side, this is my base, do not write P side or N side, let it be emitter, base and collector. Now, when I increase my VCE, collector emitter voltage is increased. So, what happens? Then we are pushing this more and more. You see, if I increase VCE from 2 to 6 volt, you see what happens? The depletion layer here is this one. This is the depletion layer at this, and this is the depletion layer at this. So, when I increase VCE, the depletion layer, this voltage is increased, pushes this way. So, when an increase in VCE pushes the depletion layer more inside the base region, as a result more and more holes, suppose it is P side, so holes, if it is N side then electrons. So, here let us assume P side. So, more and more holes manage to cross the base and come to the collector side. You see, I am not changing my this voltage here, emitter base voltage, not changing, I am keeping constant. So, that means I have kept my IE constant. So, if I keep my IE constant and if I change my this voltage between emitter and collector VCE, that output voltage if I will change, what will happen? Then more output voltage means this the depletion layer will be pushed inwards, as a result more and more holes will manage to cross this and less will be the holes which will combine constituting this base current. So, the base current will be get reduced. So, simply increasing the emitter current voltage, what we should remember is increasing the emitter collector voltage will make this come inward, this depletion layer will be pushed, and so more and more hole current will pass to the collector, and so there will be the less base current. So, let us summarize it, the input characteristic, let us summarize it. The input characteristic is similar to a forward biased PN junction. Next, in a forward biased PN junction there is only one current, but here since we are taking IB which is a small part of the emitter current, so there is only one current, so a small part of that current will also behave in the same manner. Next, once we cross this potential barrier of this junction, you see the potential barrier is positive and this barrier is here. Once my voltage crosses this potential barrier, then the current varies linearly. And next, when I vary this VCE a small amount, we see that at a constant value of VBE, the current diminishes. That means the current, the holes are able to manage this, to manage to cross over this base very efficiently. So, this is how input characteristics are there. Now, come to output characteristics. So, in output characteristic we plot a variation of the collector current IC with collector current IC with the collector emitter voltage, that is VCE, keeping base current IB constant. We keep IB constant. So, we draw a graph. Now, next we plot the graph for different values of the base current IB to get a family of curves. So, this is what we do in the output characteristics. Let us plot the curve and see it. Take down this first. So, now let us draw the output characteristics here. You see, this is along x axis we will plot VCE, that is measured in volts, and we will plot here this IC, that is in milliamps. So, what we observe, that as we increase VCE keeping IB constant, initially the current grows, IC grows linearly, and then it becomes constant nearly. So, this is for a particular value of IB, suppose 5 microamps. So, if this is the IB value, suppose this is this value. Now, what actually happens? Let us see this. This is our transistor with this as emitter, this as the base, and this as the collector. So, when you see we have put it in common emitter configuration mode, this is IB and this is the collector, this is the collector, this is the emitter. So, this is what we have CE as. That means, we have applied here voltage is suppose 0 or very small. So, that means, between these two the voltage is suppose negligibly small. Suppose this is at a volt 0.5 volts and here it is 0 volt and it is 0 volt. So, you see here this is high volts, let us take it to be minus 0.5 volts. So, what happens? This is high voltage. So, here this junction the field is here and here this from this direction. So, here this is also forward biased and this junction is also forward biased. So, what happens? Below this region, in this region both the junctions are forward biased. Both the junctions are forward biased. So, the transistor action is not taking place and the current is due to minority charge carriers or others, but the transistor action is not taking place. Now, when I increase my VCE, what happens then at some stage, that is called, this stage comes when this becomes forward biased and this becomes reverse biased, and thereafter the current IC will be nearly equal to IE and transistor action will take place, and then you will get a constant current like this. So, in this region means from this onwards region, emitter base junction is forward biased and collector base junction is reversed biased. So, we say that within this region transistor action is taking place. Let us write this whole thing. So, thus initially when VCE is increased, the both junctions are forward biased and so the current is due to minority charge carriers. So, you see this, we are talking about this stage minority charge carriers. The transistor action does not take place. So, what happens when both are forward biased? The holes will not be able to migrate to this, and so transistor action will not take place. Now, once the emitter base junction becomes forward biased and the collector base junction reversed biased, then the transistor action begins. And thus the current IC will become nearly constant. It is not constant, nearly constant. So, actually this line will be slightly growing so that we can have a resistance also. So, that means here this stage is called saturation and this stage is called active region. So, this is saturation region, active region. Now, let us see same graph if for different values of IB. Now, let us draw the graph family of curves for this. This is V collector emitter voltage, this is your IC in milliamps, and so you see here this is IB is equal to suppose 5 microamperes. Next, if I increase IB value, that is 10 microamperes, then we have a value of IB is equal to 15 microamperes. We will get such type of IB is equal to 20 microamperes like that. So, we have a family of curves and we see that this region is called active region. We will call this active region. So, in this region transistor action is taking place, and here transistor action means the emitter base junction is forward biased and the collector base junction becomes reversed biased. This region is called saturation region. That means in this region our both the junctions are forward biased and we have also at this stage a cutoff region where IB is equal to 0. So, this will be called cutoff region. That means, in this region we have both the junctions will be reversed bias. So, when IB will be 0, so we will have a cutoff region. So, this there will be 3 regions like this. Now, so this is the output characteristics. Let us summarize this. This is the output characteristic. Output characteristics. And here we have, let us summarize it, input characteristic. So, in input characteristics we have plotted V, VB and with IB, that is in microamperes, and the current was linear. Here the current increases and once it reaches this linear part. So, now by studying these graphs we here plot, this is, suppose this value is delta IB and you see this value is delta VBE. So, we define input resistance R input as the ratio of R is equal to base emitter voltage by delta IB at constant VCE. So, this is EC input resistance. We may define this as AC input resistance or DC input resistance. If I take this change, we will define as AC. If we take this ratio, I will divide at input. Here also we can define this small quantity, you see, just see this very small here, that is the current changes negligibly small. Here this is not linear, somewhat growing like that. So, there is a slope here. So, R output as delta VCE by delta IB at delta IC at constant IB. So, if I keep IB constant, then delta VCE by delta VC is the output resistance. Now, there are 4 different modes in which the transistor can be used. So, modes of operation of a transistor. There are 4 different modes in which a transistor can be used. It depends on the emitter base polarity and collector base polarity. So, depending on this emitter base polarity and collector base polarity, we can have 4 different modes of operation. So, you see here there are 4 quadrants. So, suppose we plot here this emitter base and this as collector base. So, if we have a NPN transistor, NPN, with this as emitter, base and collector, then here both these junctions are forward biased and this will be called active region. Sorry, this is forward biased and this is reverse biased. So, this is called active region. And here we have this NPN transistor. Suppose I have taken here NPN transistor. This is emitter, this is base and this is collector. So, this is in saturation mode. So, here in this quadrant you see here VCB and VEB. So, here saturation means both are forward biased and here this is N, P and N. This is cutoff region, cutoff region. So, this is your emitter, this is your base and this is your collector. Both these junctions are reversed bias. And here again we have NPN transistor with this as collector, this as emitter and this is base. This is inverted region. So, these are the 4 different modes in which a transistor can be operated. Active region where both, not both, where this region is forward biased and this is reverse. Saturation, both are forward biased, here both are reverse biased, and here this is inverted region means collector base is forward biased and this emitter base is reverse biased. This is called inverted region. These are the 4 ways in which a transistor can be used. Now, let us come to active mode. What is active mode? In active mode, the emitter base junction is forward biased and collector base junction is reverse biased. The transistor action takes place in this mode. So, when we want to use this transistor as an amplifier, we have to work in this active mode. So, the transistor as an amplifier can be used in this mode. Next is saturation mode. Saturation mode. So, in saturation mode, both the junctions, that is emitter base and the collector base are forward biased and the transistor conducts the current. So, let us see something more about this after this cutoff mode. Cutoff mode. In cutoff mode, both the junctions emitter base and base collector are reverse biased, and so the transistor does not conduct. Now, if I select my input conditions in such a way that when we have that my transistor is for some signal in saturation mode and some signal for cutoff mode, that means when saturation it will conduct and when cutoff it will not conduct. So, that can be used as a switch. That means at one stage it becomes cutoff mode. So, whenever a transistor is used as a switch, that means it sometimes in a saturation mode and for another part of the signal it is in a cutoff mode. So, very important point here. So, when transistor is to be used as a switch, then for on position it is in saturation mode and for off position it is in cutoff mode. Thus, if you work in saturation and cutoff region, that is off on state and that will represent off state, and we will have the transistor work as a switch. So, now the fourth mode, that is the inverted mode. In inverted mode, the emitter base junction is reversed biased and the collector base junction is forward biased. The collector becomes emitter and the emitter becomes collector. The role of emitter is replaced by collector and the role of collector is replaced by this. But we know that in a transistor emitter is heavily doped. So, when inverted, the collector is not heavily doped. So, it will act as a transistor, but with a very poor performance. So, thus the performance of the transistor in the inverted mode will not be like the active mode because collector is not heavily doped as the emitter. So, the role of in inverted mode, the role of emitter is done by collector and collector is doing the work of emitter. But since emitter is heavily doped and collector is moderately doped, so the efficiency of the holes, providing holes from the collector side to the base side will not be as which is in the active mode. So, the performance will be poor. So, thus there are these four modes, and in next session we will see the role of these four modes and the transistor as a device.